Many kids and even adults use trampolines in their free time. But behind this enjoyed pastime activity, there is more physics that exists than what meets the eye. When people jump on trampolines, their center of mass changes as they move up and down from the point of equilibrium. It doesn't just stay in the middle of their body. When people perform somersaults or other flips, the trampoline springs can project their bodies in such a way that the center point of mass comes off of their bodies. A free body diagram can further explain this idea. Most trampolines are made up of rubber mats that are then connected to a metal frame by coiled springs. With this in mind, a trampoline exerts spring force as well as applied force and gravitational force. As a person pushes off of the trampoline, their gravitational force is working against their motion while both the applied force and spring force push them upwards. These forces are equal only when they are balanced. Balanced forces happen when there is no acceleration. The object on the trampoline must be motionless and have a constant velocity, where the speed per unit of time is the same at the beginning of the jump and at the end of the jump. Force vectors have equal magnitude in each direction for balanced forces, but different magnitudes in each direction for unbalanced forces, which is where forces have inconsistent velocities and are in movement. Also note that the acceleration constant for gravity is negative 9.81 meters per second squared. A force using a trampoline has both potential energy and kinetic energy. A trampoline uses elastic potential energy, where the energy stored in elastic materials are the result of their stretching or compressing. If an elastic object is not stretched or compressed, then there is no elastic potential energy stored. The elastic object is said to be in its equilibrium position or zero potential energy position. In this diagram, the kinetic and potential energies are equal. The law of conservation of energy states that the energy can neither be created or destroyed. Total energy equals potential energy plus kinetic energy. As the person is ascending near the top of their jump, their kinetic energy decreases as their potential energy increases. However, at the height of their jump is where potential energy is the greatest and kinetic energy is at a minimum. As the person is descending, their kinetic energy increases and their potential energy decreases. Kinetic energy is at a maximum when the person jumping lands on the trampoline after their descent. This is also where potential energy is lowest. The formula used for kinetic energy is 1/2 times m times v squared. Ke represents kinetic energy measured in joules, m stands for mass, and v squared is the speed of the object in meters per second. Keep in mind that kinetic energy is a scalar quantity, so it does not indicate direction. Elastic potential energy takes on the formula of 1/2 times k times x squared. PE spring is the potential energy of the spring measured in joules, k is the spring constant, and x squared equals the amount of compression relative to the equilibrium position. Newton's 3 laws of motion can also be applied to the use of a trampoline. The first law of motion states that an object at rest will stay at rest, or an object in motion will stay in motion unless acted upon by an external force. If a person is just standing on a trampoline, they will not start jumping until their legs, which act as the force, allow them to experience movement. The third law of motion says for every action there is an equal and opposite reaction. This allows the spring to affect you. If you push force onto the spring, projecting you downwards, it will then exert the same initial force upwards. The second law of motion states that the acceleration of an object depends on its mass and the net force acting upon it. The formula used for this law is force equals mass times acceleration. Because gravity has an acceleration constant, if two people are jumping on a separate trampoline, the heavier person would be able to exert a greater force on the spring and jump higher than the person with less mass.